In this section, we're going to be looking at drawing two lines on the same graph at the same time. So if I wanted to, let's see, let's say I wanted to graph some lines, more than one of them on a particular axis. So I'm not going to do anything extraordinary here, but let's say we have one line comes in and goes like this, and then another line comes in and does something like this. What we're interested in is this point where they intersect, this intersection point. What that does is, whatever this point happens to be, it is simultaneously on the line going from the left to the right, but at the same time it's also on the line going straight up and straight down, close to straight up and straight down. This is the point we're going to be looking at. And the idea is we're going to graph two lines on one graph and find out where they intersect each other. Let me do an example to illustrate this process. Y equals negative 1/2 x plus 1. Y equals 2x plus 6. Let me go ahead and throw a graph down and graph both of these lines. So I got my graph down. Starting with the first line, the y-intercept is 1. So I'll start at the origin and go up 1 unit to put that y-intercept there. From that point, I'm going to use the slope to generate more points. So negative 1/2 means to go down 1 and to the right 2. So from this point, I will go down 1 and to the right 2. I'll continue this process so that I have more accuracy in my graph. You'll see why that's important in a minute. And I'll back up and do the same thing in the other direction. So I'll go up 1 and to the left 2 just to generate points on the left side. Now, the reason I do so many points is it's for my own personal use. It's not something that I expect everybody to do. But when I go and connect the very farthest point from the other very farthest point, all the points in between will line up. And let's see how accurate that was. It looks to me like it's a teeny bit off, especially all my points. So it takes a little work to finagle this in. And then once you get it, you feel like you got it. Sometimes it moves on you. But nonetheless, there's my line. And you can see some of my points were plotted better than others. But nonetheless, let me go on to the next one. Y equals 2x plus 6. This 6 right here is the y-intercept. So starting at the origin, I'm going to go up 6 units. 1, 2, 3, 4, 5, 6. And then the 2x tells me that the slope is 2 over 1. So I'll go up 2 and to the right 1. So up 2 and to the right 1. Well, I've run out of graph. So I'll reverse my steps the other way. Down 2 and to the left 1. 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 And keep going until I feel like I have enough. Like I said, you don't have to do this yourself, but I'm going to connect this very far distant point to this distant point, and all the points in between will line up. So let me go ahead and do that. Starting at this point up here, so I can expect that it's like you're using your ruler right now, and you go and match up that far away point with this far away point. I do it especially with the ruler. I find that my work is more accurate if I do it this way. Let's see here. I think I'm good. So now what we want is the intersection point. So if I look right here, that point is -2, 2. -2 for x, +2 for y. That's the solution to this system of equations. We're looking for one point that happens to be on both of these lines at the same time. I'm going to check this just to show you that it works. So up here, let me do a check. And we'll start with y equals -1/2 x plus 1. I'm going to take these numbers and plug it into that equation. So x will get -2 and y will get +2. Those 2's cancel. And once I get to the point where I'm certain that I've correctly solved it, I'll put a check mark. So that one checks. Let me do the other one. And y equals 2x plus 6. Let me replace x with -2 and y with 2. So once I see that 2 actually does equal -4 plus 6, I know it's checked. So this is the thing that I'm looking for, a single solitary point where both of the graphs go through it simultaneously. Let's try y minus 2x equals 2, and the other one is 4x plus 3y equals -24. So in order to graph these things, the first thing I'm going to have to do is change them to slope-intercept form. The first equation is very easy to do that with. Second equation takes a little more work. The second equation, I'll subtract the 4x first. So I get 3y equals -4x minus 24. And then I'll divide by 3 to get y equals -4/3 x minus 8. So what I'm going to graph are these two equations. Let me put them over here. These are the ones that I'm going to graph. Y equals 2x plus 2, and then y equals -4/3 x minus 8. That minus 8 is a y-intercept that's down there a ways, so let me get myself a big graph, especially with a lot of negative for y in anticipation of that particular line. I'm not really sure how far I need to go with this thing, but I'm going to give myself a super lot of distance. I got to get it to lock on that grid. There we go. All right, now let me go ahead and throw in my lines. Y equals 2x plus 2. The y-intercept is 2. So starting at the origin, I'll go up 2. And now the slope is 2/1, so I'll go up 2 and to the right 1. And I'll continue that for a little while so that I get more accurate lines. I'll reverse myself the other way, down 2 and to the left 1. Oh, I guess that's about enough. Will it even fit on a page? Yes, it will. Good. So let me go ahead and get a line that connects those things. So starting way down there and stretches way, way up to there. I think I got it right fast. Very nice. All right. The second one has a y-intercept of -8. So Starting at the origin, I'm going to go down 8 units. 1, 2, 3, 4, 5, 6, 7, 8. Way down there it is. And the slope is negative 4/3. So I'm going to go down 4 and to the right 3. So I need even more space. Down 4 and to the right 3. So I go down 4, 1, 2, 3, 4, and to the right 3, and I'll put a dot. That's off the graph. So it'll continue down this way, but I'll reverse my steps. If I went down 4 and to the right 3, if I reverse my steps, I'll go up 4 and then to the right 3, and I'll put a dot here. And if you're paying attention, I can see this is the point where they're going to intersect anyways. I'll keep doing this, 2, 3, 4, 1, 2, 3. And the next one would run off the graph anyway. So now let me connect those things with a line. Oh, see, it goes off a little bit on me. Do I have what I'm looking for? It sure looks like it. This point right here, let's see what it is. If I start from the origin and I go to the left 3 units, so x is negative 3, and y is 1, 2, 3, 4. Y is negative 4, so the x was negative 3, the y was negative 4, so negative 3 comma negative 4 is our solution. All right, next one we have 3/4 x minus y equals 0. And then I have 3x minus 4y equals 20. So if I want to graph these things, I'm going to have to solve them each for y. For this one over here, it's very simple. Just add y to each side and you get y equals 3/4 x. So let me start my graph with that one. I don't know how much graph I'll need, but I can always make it bigger if I have to. 3/4 x, imagine there's a plus 0 there so that you know that you start at the origin, right? So your y-intercept for that one will be the origin, and from there you're going to go up 3 units and then to the right 4. So up 3 to the right 4, up 3 to the right 4, 1, 2, 3, 4, good. And let me reverse my direction. So I'll go down 3 and to the left 4, down 3 and to the left 4, and let me go ahead and connect those with a line. Does that look all right? It looks a little bit off to me, so let me fix it. This, of course, mimics the effort you're going to have to put in to make sure your lines are graphed well. Still not. Now, for the other one, let's first subtract the 3x. You get negative 4y equals negative 3x plus 20. And then when I divide by negative 4, I'll get y equals 3/4 x minus 5. So I'll start by going down 5 units to graph the y-intercept. There it is. And from there, I'm going to go up 3 and to the right 4. So up 3, 1, 2, 3, and to the right 4. Up 3, to the right 4. Up 3, to the right 4. Down 3 to the left 4. Let me go ahead and connect those. I think I have my best luck if I just stop it right at that particular point. It has no choice but to be right there, does it? But you'll notice, oh, look at that. It is, I think I have done something wrong. Let me see, starting here, 1, 2, 3, and then 1, 2, 3, 4. Did I do something wrong down here? 1, 2, 3, 1, 2, 3, 4. No, why is my graph all wrong then? Let me see if I did it. Ah, right there. See that? That point there should have been there. See, when I went from this one here, or let's check this one here. Starting from here, I went up 3, 1, 2, 3, and then to the right 4. Ah, see, that point was wrong. That means this point over here was wrong. 1, 2, 3, 1, 2, 3, 4. There was my ending spot. So let me fix this. And so this is the beauty of drawing all those points. You can see when you're off. So let me fix my graph by getting it right on that point there. And let's take a look. Now it looks like it goes through all my points, so that was a good fix. Let me erase these extra points that are hanging around. And it looks good. Well, they're not connecting. They're not intersecting. And I don't know if they're ever going to intersect, because who's to say that somewhere way, way, way off, they don't touch. They get so close. It's so slow how close they get to each other that you can't even perceive it. Well, we know that's not the case. How do we know that? Right here, look at this. And right here, they have the same slope. Same slope means parallel lines. So when you have that, since there's no intersection point, the only answer we can put is no solution. That's actually what we'll put for the answer. So when they don't intersect, you have a situation like this where you've got parallel lines. You should have been able to tell right off the bat just by looking at the slope. I didn't really need to go any farther, but I wanted to go through with the problem to show you what you can come up against. And now a system like this, such a system of equations is called inconsistent. Those with no solution are called inconsistent. Let's try another example. This time we have y equals 1/3 x minus 2, and we have 4x minus 12y equals 24. So the first line, I've already got what I want, so let me go ahead and graph it. That one's easy. The y-intercept is -2, so I'll go down 2 units and put a dot. And then from there, I'll go up 1 and to the right 3. So up 1 and to the right 3. Up 1 and to the right 3. And I'll do that for a little bit till I feel comfortable. Down 1 and to the left 3. Down 1 to the left 3. Down 1 and to the left 3. That should be enough. Let me go ahead and put my line through there. Starting at this point here. and ending at that point there. Gotcha. All right, and the second one, well, let me go ahead and start to get y by itself. So I'll get negative 12y equals negative 4x plus 24. And then I'll divide by negative 12. So I'll get y equals negative 4 over negative 12 is 1/3. And then when I divide by negative 12 into 24, I'll get negative 2. Well, I can stop right there. If you look, this line is exactly the same as this line. So when I graph this line, it's just going to be the same one again. That means the line, well, every single point on the line is a solution. So every point on the line is a solution. I suppose you could think of it as, if you thought of these as two lines, every single point on each line is on the other line at the same time. So every point on the line is a solution. So what we write for our answer is simply this. Since every one's a solution, well, there's an infinite number of points on the line. So we simply write an infinite number of solutions. Now, I want to do, before I leave this section here, I would like to do one more problem. And it goes like this. So my system of equations this time is 2x minus y equals 1 and 3x minus 4y equals 12. So as before, I will solve the first equation for y and to get it into slope-intercept form. This, I'll subtract 2x, so I get negative y equals negative 2x plus 1. And then I'll divide by negative 1 to get y equals 2x minus 1. So let me go ahead and graph that thing. Hopefully that's enough graph. The y-intercept is negative 1, so I'll put a dot at that spot. And then from there, I go up 2 units and then to the right 1. So up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. And reverse my steps, down 2 and to the left 1. Let me go ahead and put my line connecting all of these points. I think we're on there. And then for the other line, let me go ahead and solve for y. I'll subtract 3x, I get negative 4y equals negative 3x plus 12. I'll divide by negative 4 to get y equals 3/4 x minus 3. So this has a y-intercept of negative 3, so I'll put a dot at that y-intercept. From there, I'm going to go up 3 and to the right 4. So up 3 and then to the right 4, up 3 and to the right 4, and down 3 and to the left 4. I think that'll be enough because they're going to cross once I draw this second line. So let me go ahead and throw that in. And there they are. So this point of intersection here it is. I wonder if it'll let me zoom in on this thing. Yes, it will. Here we go. There we are. See this? It's not at a good spot. Like I would have liked it there. I would have liked it there. I would have liked it there. Practically anywhere besides where it is. This spot does not happen on a nice corner spot. So what do we do? So we're stuck on something like that. I can't actually do it with graphing. Let me get this back to the size, the normal size. And this intersection point is no good. Let's call it an inconvenient intersection point. The problem with graphing is that if they don't line up and hit nice spots, like corner spots and everything like that, then you're stuck. You have to come up with a different method. And that's what we're going to do in our very next section. So let me go ahead and start that one. We're going to solve systems by substitution. And let me go ahead and get my my lines in place. I'm going to drop the graphical and go with more like these because we already know that it doesn't have a solution that I can do with the graph. So let's do this example again. We have 2x minus y equals 1, and then we have 3x minus 4y equals 12. Now I don't intend to graph these, but what I do want to do is look for any of these in here that looks like it's easy to solve for one of the unknown quantities. So yeah, I don't know the value of x or y, but it looks to me like it's easiest to get this y right here by itself. So I can do that as before. I can subtract 2x, negative y equals negative 2x plus 1, and then I can divide by negative 1 to get y equals 2x minus 1. Now, I understand that that's set up for graphing, but that is not what I'm going to do. What I'm going to do is take this quantity here, and I am going to take it and substitute it right in for that particular y there. So substitute this quantity into the other equation. So substitute y equals 2x minus 1 into 3x minus 4y equals 12. So I'll replace the y with 2x minus 1. So 3x minus 4 times 2x minus 1 equals 12. See it in there? The y has been replaced. Now I have one unknown quantity, which is the x, and one equation, which I can do. So I get 3x minus 8x plus 4 equals 12. That gives me negative 5x plus 4 equals 12. Subtract 4, I get negative 5x equals 8. And divide by negative 5. And there's the value of x. Now, take this quantity and plug it back into this first equation. So for the y value, the y equals 2x minus 1. I'm going to replace the x with negative 8 over 5. And when I do that, let's see, I don't know why I put a negative in front of there. No reason. I have negative 16 over 5. The 1 I'm going to change to 5 over 5. And I get negative 21 over 5. So my answer is negative 8 over 5 and negative 21 over 5. If I were to write them as decimals, which I don't recommend you do, just leave it like this, they would be negative 1.6 and negative 4.2. What I would like to do is go back to the other, when I graphed it, and let's see if that makes sense. Could x have been negative 1.6? Well, if you take a look, there's x equals negative 1, there's x equals negative 2, and it's a little bit between, the x values between negative 1 and negative 2. Let me put a dash where I think it is. So it could be negative 1.6. The y value was negative 4.2. So let me go to the right here. The y value would have been right about where I'm drawing this line here. But that is, let's see, negative 1, negative 2, negative 3, negative 4. It's a little beyond negative 4, so negative 4.2 would have been there. So the problem is that these numbers do not line up nicely on a grid. And so that's why we have other methods of solving these things. You can't do them all graphically. So now that's where we're going to change our focus to. As another example shows, I want to solve 3x minus 2y equals 9, and then y equals 4x minus 1. Something like this, you should sort of rejoice a little bit, because I've already have one of these unknown quantities is solved for. So I can simply take this 4x minus 1 and plug it into the first equation. So the first equation, what do we have? 3x minus 2y equals 9. I will replace the y with 4x minus 1. And then I'll go ahead and work this. I'll get 3x minus 8x, it's almost similar to the last problem, plus 2 equals 9. Negative 5x equals 7. I did two things at once there. X equals negative 7 over 5. And then you get the y value, plug it back into the first, plug it back into the other equation. I'll just say plug into the other equation. Do not plug it back into the same equation. Otherwise, it'll just zero itself out. So let me go ahead and plug the number that I got into y equals 4x minus 1. So I'll replace the x with negative 7 over 5. And we get negative 28 over 5. The 1 I'll change to 5 over 5. And we get negative 33 over 5. So our answer is negative 7/5, negative 33 over 5. Let's do another one. This time I have 2y equals x minus 3, and then I have negative 4x plus 3y equals 10. So this time I almost have y solved for, but I could make this a little easier on myself. Look at the x. I could actually take this first equation, add 3 to both sides, and I find it was easier to have x by itself than it was perhaps for have y, because you divide by 2, you're going to get fractions, and I'm not sure I'm ready to deal with that. So let me put the 2y plus 3 into the second equation. So we're going to substitute x equals 2y plus 3 into negative 4x plus 3y equals 10. So I will replace the x. I'll have negative 4 times 2y plus 3 plus 3y equals 10. So I get negative 8y minus 12 plus 3y equals 10. Let's see what else we have. I say negative 5y. I'll add the 12 at the same time. In here, we have another answer where y is involved. So I get negative 22 over 5 for y. And then the x value so if I do that, I'll have 2 times negative 22 over 5 plus 3 equals x. I'll get negative 44 over 5 plus, I'm going to change the 3 to 15 over 5. And so that'll be negative 29 over 5. So it looks like my answer is negative 29 over 5, comma, negative 22 over 5. All right, let's do 42x plus 7y equals 4, and y equals negative 6x plus 9. So whenever you see it like this, it's very nice because it's easy to tell what to plug into what. I'm going to plug in the second equation into the first equation. So my first equation, 42x plus 7. Let me replace the y with negative 6x plus 9. And that's supposed to equal 4. So my first equation, there it is. All I've done is replaced the y portion of it. Let me continue. I'll get 42x minus 42x minus 63 equals 4. The 42x's cancel, and I get negative 63 equals 4. Well, that's a bad sign. Here, what happens, obviously, negative 63 does not equal 4. We've arrived at a false statement. So what this tells you is that there is no solution. Let me make my U better. There is no solution to this problem. And let me kind of show you why. And this first equation, if I go and solve for y, I would first subtract the x's and then divide by 7. Here's where the problem lies. You see the slope on this line is negative 6. The slope on this line is also negative 6. And they have different y-intercepts. They're parallel lines. And what do we know about parallel lines? They do not intersect. So here's the situation. You have two basically just parallel lines. I've drawn them incorrectly. Maybe I should probably, let me control Z those off of there. They're actually both have a negative slope. So they go like this. One goes like this and the other goes like this. They'll never cross, obviously. So when you arrive at a situation like a completely false statement like this, you know that there's no solution. Let's try another one. We have 10x minus 4y equals negative 2, and negative 5x plus 2y equals 1. Now this is weird because I don't have anything solved like the last one. It's not to me obvious what I should plug into what. So I basically have to take one of these equations and solve for one of the unknown quantities and plug it into the other equation, and I don't see anything that looks particularly desirable. I guess this second equation here, let me see how far I need to go. 2y equals 5x plus 1. And then to get y by itself, see, I don't see, if I saw a 2y up here, I would just take and plug that in, but I don't see a 2y up there. Instead, I see a 4y. So I guess I'll have to solve for y and get 5 halves x plus 1 half. So now I have to take this, and don't forget to plug it into the other equation. So plug into the other equation. Never plug it into the same equation. So let's see what happens when I do it. The other equation is 10x minus 4y equals negative 2. So I'll replace my y with all that stuff. So 10x minus 4 times 5 halves x plus 1 half, and all that equals negative 2. So 10x minus. Now when I multiply 4 times 5 halves x, I'll end up getting negative 10x. And then 4 times 1 half is negative 2. Well, now the x's go away, but we end up with a situation like this. This is much better. Negative 2 does equal negative 2. That is a true statement. So what is this supposed to mean? Well, what happens here, if I go and solve the first equation for y, go ahead and try it. If I solve the first equation for y, I'll get exactly the same as the second equation. These two things are the same line. So with that, you know that every point on the line is a solution. So what is my answer? An infinite number of solutions.